Welcome to Sweet Spot Maths, the gold standard for A-level maths teaching. I'm David Forster. This is the second part of the lesson on the modulus function. In this lesson, I will go over 3 questions which have been set in recent years in examinations. All of these questions have their tricky parts that many candidates get wrong. Remember, it's by getting the questions right that most candidates get wrong that you will gain the examination edge. The first question here is from the OCR 2020, paper 1. So we're shown in the diagram the graph of y equals the modulus of 2x take 3. And we're asked first of all, for 2 marks, to state the coordinates of the points of intersection with the axes. You will know by now, coordinates means we need both coordinates, not just one or the other. So we think, okay, when x is 0, y will be 3. So we have the coordinate 0, 3 with the y-axis, and the vertex is going to be when the part inside the modulus is 0, 2x take 3 is 0, x is 1.5, the coordinate is going to be 1.50. We give both coordinates. Okay, now the next part of the question is very similar to the one we had in the first part of the lesson at the end, where we had a straight line with a variable gradient. If you remember in that question that the examiners said that hardly any candidates got it right. So we're given now the graphs of y equals modulus of 2x take 3. That's the one given in the graph. And y equals ax plus 2 are going to have 2 distinct points of intersection. So I've drawn in red the line y equals ax plus 2. The y-intercept is 2, the gradient varies, that's a, that's a parameter. For some a values it will not intersect the V-shaped modulus graph. For one particular a value it will touch the vertex, and for other values it will touch, or cut rather, in 2 places as it does here. The question says, find the a values where there are 2 distinct points of intersection. Thinking graphically and visually, the best way of tackling this is to find what the a value would be if the line just touches the point 1.50, because then if a is greater than that value, there will be 2 points of intersection. So we're going to plug into y equals ax plus 2, the point 1.50. We do that. And we get a as minus 4/3. So a must be greater than minus 4/3. How great can it be? Well, if a continues to increase, there will be 2 points of intersection, and that will continue up until the point when y equals ax plus 2 becomes parallel to this part of the modulus graph. In other words, when a equals 2. So thinking graphically and visually, the final answer we want is that a will be larger than minus 4/3 and less than minus 2. The lesson here being think visually, think graphically, and make sure in your answer, this time we do want it in one part. It is one range of a values that we want, and we do want strict inequalities. B part 2 says, find the x coordinates of the points of intersection of these graphs, giving your answers in terms of a. So if a is in the correct region, that is between minus 4/3 and 2, it will intersect in 2 places, here and here. We can find those by using the positive and negative values of 2x take 3, the 2 sides of the modulus function. So first of all, one intercept will be when x is bigger than 1.5. We solve the equation and we get x is 5 divided by 2 take a. Can 2 take a be 0? No, a cannot be 2. We've already said it's in the range where a is less than 2. On the other side, x is less than 1.5. Therefore, we solve this equation and we get x is 1 over 2 plus a. Can 2 plus a be 0? No, it can't. A cannot be minus 2 because it's in the range from minus 4/3 to 2. So our answer is this and this. These are our two answers. Now you could solve those equations by setting mod x plus minus 2, 3, mod of x 2x minus 3 equals ax plus 2 and squaring. You can do that. It will give you the answers. Just remember that squaring sometimes gives rise to false solutions. So you need to check carefully that your answers are valid. And also in this case, it is less simple than solving the two linear equations. On to this next question. This question, we have a graph with equation mod of 2x take 3k. K is a positive constant. It's a parameter. We're asked to sketch the graph with equation y equals f of x, when it is k, take away the modulus of 2x take 3, stating the maximum point and any coordinates where the graph cuts the coordinate axes. So we think visually, what's going on here? Well, we are doing k minus the original graph. The minus will reflect the graph in the x-axis, and the k, being a positive constant, will move it up. So we're expecting a graph which is the other way up and its vertex being a little higher. So I've drawn that here. The graph is the other way up and the vertex is a little higher. Let's check on where it cuts the coordinate axes. When x is 0, we've got k minus the modulus of 2 noughts take 3k, which is minus 2k. When y is 0, we're doing k take away mod of 2x take 3k being 0. Mod of 2x take 3k will equal k. So k is, x is k or 2k. The maximum point is midway between the two. So it's 3 over 2k and the y value is k. I wrote down 0 first of all. That was a mistake. I've left it there just to show you the sort of things you ought to check carefully, that you don't accidentally write down 0 where you mean something else. And the intercepts, we need the coordinates. They're written down here. Okay, part B of the question. Find in terms of k the set of values of x for which k take away the modulus of 2x take 3k is bigger than x take k. I've drawn the line y equals x take k on the same axes. It's in blue. K is the same constant. So this is going to cut the y-axis at minus k and have gradient 1. It also goes through k0, since the gradient's 1, and seems to cut in 2 places. The question says, find the set of values for which the modulus graph is larger than the blue line I've drawn. It seems to be clearly between here, which is k, and here, which is at the moment unknown and needs to be found. So I'm going to solve the equality for x is greater than 3 over 2k. In other words, it's to the right of the vertex. I write down the equation and solve, and I get x is 5/3 of k. On the other side, it seems fairly clear that the point we want is going to be k, but I've solved the equation anyway, and I do indeed get x is k. So we need x to be between k and 5/3 of k for this inequality. It says write your answer in set notation, so what we'd do here would be x colon such that x is larger than k and less than 5/3 k. Think graphically here, when is one graph above the other? Part C of this question. Find in terms of k the coordinates of the minimum point of the graph with equation y is 3 take 5 f of a half x. This is about transformations of graphs. We're taking f of x. We want to find where the minimum point has gone when we replace x by a half x, multiply by minus 5, and add 3 in that order. So we start. Replacing x by a half x is a stretch times 2 in the x direction. That means the vertex 3 over 2k k will go to 3k k. We're then multiplying by minus 5, which is a stretch times minus 5 in the y direction, so the vertex goes to 3k minus 5k, and then we're adding 3, which will translate the graph 3 units upwards. So we end up with 3k, 3 take 5k as our maximum turning point or vertex. Do note the first two steps could have been done in either order. It doesn't make any difference which order we do it in, but adding 3 is the thing we need to do last. The third and final question I'll go over is this one here. It says in this question, you must show detailed reasoning. For every examination board, there will be some questions where they will ask for detailed reasoning. They need to see all the steps. So if you solve this equation just by writing down the answers and got the correct answers, you should expect to get 0 marks. So solve the inequality. Mod of 3x take 2 is less than or equal to mod of 2x take 6. So I'm going to show two different solutions here, the first of which is graphical. I've drawn the graphs of y equals modulus of x take 2 and y equals modulus of 2x take 6. And we're going to need to know the points at which these two graphs intersect. These are both to the right-hand side of the vertex 2. For the other one is to the left of 3 and the other is to the right of 3. So intercept 1 we would find by setting x take 2 to equal 6 take 2x and solving. The second intercept we would find by setting x take 2 to equal 2x take 6, which is x is 4. We want the black graph to be underneath the blue graph. Therefore, my final answer is at x is less than or equal to 8/3 or x is greater than or equal to 4. Make sure that you use the equals to inequality here. It can be at the intercept points. And since they are two separate areas, you use or, not and. Alternative method here. We could, I've said normally squaring both sides is not a good method. Here, it will be absolutely fine because both sides are positive. So squaring both sides, a positive number less than another positive number, square them. The first square will still be less than or equal to the second square. Multiply out, make it into a quadratic, and note that the answer is going to be when x is less than or equal to 8/3 or x is greater than or equal to 4. Generally speaking, squares can give rise to false solutions, but in this particular case, we're okay since both sides are positive. The examiners do actually say for this question that those who squared tended to get the answer correct better than those who didn't. And that's fine. Right, part B of the question. We are still in a question where we need detailed reasoning. It says, give full details of a sequence of two transformations needed to transform the graph of y equals mod of x take 2 to the graph of y equals mod of 2x take 6. That is, back to these two graphs to transform this one into this one. Now, there are two ways of doing this, two things you need. One is going to be a stretch, and one is going to be a translation. You can do that in either order. So what you could do is you could stretch by scale factor 2 in the y direction, which would give y equals 2 times mod of x take 2, which is 2x take 4. Then replace x by x take 1, and you get the graph that we require. You could alternatively have done these things in the other direction, in the other order. First of all, translate one unit to the right, and then stretch by scale factor 2 in the y direction. There's a third possibility here. You could have done a stretch in the x direction. I've not listed that, but that also is fine as an answer. This is a detailed reasoning question, so you need to actually explain why these transformations are correct, as I have shown. Also, make sure you use the correct terminology. Use stretch and translate. Don't use informal equivalents like move or shift. The examiner does want to see that you can use the correct terminology here. So here we have the examination mark scheme. They say the question was, part A was done extremely well. Nearly all candidates correctly solved it. Two things I will say is, trying to solve equations, linear equations, without a graph leads to trouble. So if you are going to solve it using equations as I did first, make sure you've got the graph here. Here the quadratic method works well, but elsewhere can lead to fake solutions. It's also worth noting what the examiners wanted as the answers. There were only 3 they accepted. The first one is listing it as I listed it, without set notation. If you use set notation, this is an OR situation, so you have to list 2 areas separately, not combine them. So these were the answers that were wanted by the examiner if you use set notation. If you are going to use infinities, make sure you use a curved bracket at the end, not a square bracket, to show that infinity is not included. Infinity is not a number. All it means is carry on going without limit. That's it for this lesson on the modulus function. I hope you've learned from it, and by learning to do maths in the sweet spot, which is fine-tuned for you to achieve A star without wasting time, to learn to shift your perspective and think like a mathematician and complete even the hardest exam questions correctly and confidently. One thing this means is, when you've done a question, what can you learn from it to do the next question? So next time you will have learnt something and do it correctly. And the third thing is, by knowing the examination secrets, the gaps, mistakes and omissions of most other candidates, you can get the examination edge and those final few marks that will get you the A star. If you would like further information on sweet spot maths for A level, you can contact me on support@davidforster.org.uk, and I'll be delighted to send you some further information on sweet spot maths. Thank you for participating in this lesson.